An object can have kinetic energy due to translation, 1/2 mv squared, as well as a separate rotational kinetic energy given by 1/2 I omega squared. When an object rolls without slipping, both forms of kinetic energy are present. The condition for rolling without slipping is that the angular velocity omega be equal to the translational velocity divided by the radius of the object, r. The total kinetic energy is thus 1/2 mv squared plus 1/2 I omega squared, or 1/2 mv squared plus 1/2 I times v over r quantity squared. Different objects will have different moments of inertia. The three objects we will look at are the hollow cylinder, a segment of PVC tubing, the spherical hollow shell, a racquetball, and the spherical solid ball, a bocce ball. The hollow cylinder has the largest moment of inertia given by mr squared. The hollow shell has moment of inertia 2/3 mr squared, and the solid ball 2/5 mr squared. An easy way to keep track of these is to let f represent the fraction 1, 2/3, or 2/5, depending on the object. Then the total kinetic energy will be 1/2 mv squared plus 1/2 f times mv squared, since the r's cancel in the second rotational kinetic energy term. Imagine an object rolling down an incline at angle theta. If the object begins at the top of the incline with 0 kinetic energy, and we define the top to be 0 potential energy, then it gains kinetic energy as it rolls downhill, and the potential energy becomes negative relative to where it started. The kinetic energy at any point is the combination of translation plus rotation. The potential energy may be related to its position d along the incline. Potential energy will be minus mgy, but y is just d sine theta. Thus the total energy will be translational, 1/2 mv squared, plus rotational, 1/2 f times mv squared, plus the negative drop in potential energy, minus mgd sine theta. D is the quantity that a motion sensor aimed down the slope will measure for position. By conservation of mechanical energy, we expect the total energy to remain constant all the way down the hill. If we were to plot just kinetic energy, we would expect it to increase as the object picks up both translational and rolling kinetic energy. The potential energy decreases toward larger negative values. The total energy, which is the sum of kinetic plus potential, is expected to remain constant. One easy experimental trick is, instead of measuring the angle theta to determine the sine of theta, just measure the rise of the track and divide by the length along the track. This ratio can always replace the sine of theta in calculations. Here you can see that when L is 100 centimeters along the incline, the rise of the track should be measured to the bottom edge of the track, since the bottom edge is in contact with the table when L is at the 0 centimeter mark. In this case, since h is approximately 8 centimeters and L is 100 centimeters, the sine of the angle is the ratio 8 divided by 100. Now place the PVC cylinder in the track, carefully aim the motion sensor down the incline, and let the cylinder roll. Here is the position data from the motion sensor. It looks pretty good until the end, when the cylinder ran into the end stop and the motion sensor lost track of it. If you open a data table and select the data of time and position, you may copy and paste it into graphical analysis. You can then trim off any data that you have reason to believe is suspect. We need velocity for the kinetic energy calculations, so begin a new calculated column called v and use the derivative function from the calculus list of functions. The definition needs to be the derivative of position with respect to time. Add the translational and rotational kinetic energies to get the total kinetic energy. Here we calculate the energy per unit mass, so we don't have to weigh the object and assume a mass of just 1. The 1.0 in the second term represents the fraction f in the moment of inertia of a hollow cylinder. This number can be changed for other objects. The potential energy per unit mass is just the negative of g times position times the sine of the angle theta, here just the ratio 8/100. The total energy per unit mass is the sum of kinetic plus potential energies per unit mass. Here's a plot of kinetic energy in green, increasing as the object picks up speed down the hill. Potential energy in yellow, dropping as the object loses altitude. And total energy, which ideally remains constant. We can quantify to what extent the total energy remains constant by determining the standard deviation in total energy, a measure of its variation, and comparing with the total amount of available energy, best measured as the maximum kinetic energy. The percent error is thus the standard deviation of energy divided by the maximum kinetic energy times 100%. Repeat the experiment with the racquetball, considered a hollow sphere. In the analysis, don't forget to change the value of f to 2/3. Notice the use of the meter sticks to guide the ball down the middle of the track without providing too much friction. Then repeat with the solid ball with f at 2/5. Mostly have fun with this lab and don't get hurt.